Sounds good.
All right. Welcome everybody to this week's GOCC. We're super excited to have Patty Cummins from University of Minnesota speaking. Before I introduce her, I want to remind everyone of our community statement of the seminar. So we have sort of 3 principles. 1 is that we're all learning. 2 is that everyone has something to contribute. And 3 is that no one has all the answers. So we think of this as including the audience and the speaker. And yeah, so we're very, very excited to have Patty Cummins from University of Minnesota, who will be talking about the invariant theory of the free left regular band.
Thank you, Sarah, and thank you to all the organizers for putting the seminar together. Yeah, today I'm excited to tell you about a project I've been working on with Sarah Bronner, who you just heard, and Vic Reiner. And like she said, it's about the invariant theory of the free left regular band. And today's story is going to start with a surprising connection between card shuffling and hyperplane arrangements. And this is work of Bidiger, Hanlon, and Rockmore in the 90s. And they used the geometry of hyperplane arrangements to help understand the eigenvalues of certain shuffling operators. And this was a really exciting and celebrated result, and soon after it became generalized to a larger setting by Ken Brown, namely the setting of left regular bands. So we'll go over his generalization and focus our attention on a particular example of a left regular band called the free LRB. And then we're going to shift gears a little bit to think about left regular bands that have an additional algebraic structure, namely some group acting on them. And in this situation, motivated by invariant theory, there are more questions that we can ask. And our free left regular band will be an example of such an LRB. So that will bring us to our research, which is answering these invariant theory questions for the case of the free LRB. All right, so let's start with some card shuffling. And the operator we're going to talk about is called random to top. And so in this setting, we're going to think of having n labeled cards. We'll call them 1 through n. And the way you shuffle is maybe a little bit strange. You're going to pick some card at random from your deck. Everyone has the same probability of being chosen, and then move it to the top. And you can do this over and over again as many times as you'd like. But we're going to try one iteration of this to get our notation down. So imagine we just have 3 cards, 1, 2, 3, and we start at this state, 1, 2, 3. So by this, I mean that card number 1 is at the top of the deck and card number 3 is at the bottom. We write this to mean that there's like a 1/3 chance that we pick card 1 to put back on top. So there's a 1/3 chance we'd land in this state. Similarly, we could pick card 2 with probability 1/3 and land in this state, or just as likely, pick card 3 to end in this state. So this is like one shuffle applied to 1, 2, 3. And we are going to think about these shuffling operators as matrices. And so the rows and the columns will be both indexed by all the possible orderings of our deck. And you can think about the columns as telling you if you start with a given state, this column is the probability distribution of where you'd end up by applying one shuffle. So this blue column here corresponds to this sum. And so card shuffling is an example of a Markov chain. And one popular question people are interested in for Markov chains is how long does it take to get close to your long-term behavior that you'd expect? So with normal card shuffling, like where you treat the cards equally, like random to top does, this comes down to asking basically how many times do you need to shuffle your card deck for it to be well mixed? And to answer this question, people are often interested in the eigenvalues because this can help bound this rate of convergence. So this is a popular question for combinatorialists, is to find the eigenvalues of different Markov chains. And it turns out that one way to do a lot of these at once involves hyperplane arrangements. So a hyperplane arrangement is a collection of n-1 dimensional subspaces of some n-dimensional space. This is going to be our example throughout today. You might recognize it as the Braid arrangement that goes with the symmetric group on 3 letters. And in this example, n is 2, so our ambient space is the plane R2, and our hyperplanes are these 3 lines. And it turns out that when you have a hyperplane arrangement, you can chop it up into smaller pieces that are called faces. And so with our example, there are 13 faces. We have the origin in the middle, 6 rays throughout, and then also 6 chambers. And the chambers are going to be really important today. And the way you can think about chambers is if you have a hyperplane arrangement, just get rid of all the hyperplanes, and then your original space will be broken into connected components, and those will be your chambers. And something that I think is very surprising about these spaces is that they actually have a multiplicative structure. So the way the multiplication works is like this. Say that this blue ray here is called F, and this pink ray here is called G. The way you get face FG is you start somewhere along face F, and you take a tiny step towards face G. And you're going to end up in some potentially new face. Here, in this case, it's this like pink, well, I guess there's multiple pink chambers, but it's this one with the star. And then this is called face FG.
I have a quick question about this multiplication.
Yeah.
If I'm already in one of the big chambers, because I'm only taking a tiny step, I presume I can't ever get out of the big chamber?
Exactly. Yeah. And that's a great point that will come up in a second. Yeah. If you start in a chamber and you multiply times, or I guess this is related to a point that we'll go over. Yeah. If you started a chamber, you're going to stay in that chamber. Yeah. Because you're taking a very small step. This is a little bit of a loose definition, but it's, I think, the easier one to see.
Sure. Thank you.
Yeah. All right. So that is the face semigroup. And we're actually going to be more interested in the face semigroup algebra. So as a vector space, this is just C linear combinations of the faces. And multiplication behaves like how you'd expect. So in particular, if you've seen the group algebra before, it's a lot like that, where the constants will commute with the faces. And then like when you have 2 faces, multiplication, it just works the same as in the semigroup. And so like we said, this chamber subspace will be really important. And so we're going to call it C gamma. And it turns out that it's closed under left multiplication by the face algebra. So this is kind of related to the question just brought up. But instead, if you take any face and multiply it by a chamber, you're going to land in some chamber. So this forms a module over the face algebra, and we're going to call this the chamber module. Sorry, there's cats running around. All right. Okay, so we said that like shuffling connects to hyperplane arrangement. So let's see an example of this in action. If you are familiar with the Braid arrangement, you might know that you can actually label these chambers by permutations. And so I claim that if we like call this ray F1, this ray F2, and this ray F3, the face algebra element 1/3 F1 plus 1/3 F2 plus 1/3 F3 is going to act like random to top on the chambers. And so let's do an example. And to be consistent, we can multiply it again by the chamber 1, 2, 3 to kind of match our card deck where 1 was on top, 2 in the middle, and 3 on the bottom. If we do F1 times 1, 2, 3, that's taking a step off of this face into this chamber. So we get 1/3, 1, 2, 3. If we multiply F2 times 1, 2, 3, that's starting at this face, taking a tiny step towards the chamber 1, 2, 3, and we end up here. And finally, if we start at phase 3, take a tiny step, we're going to end up in the chamber 3, 1, 2. So this should look just like the computation we did at the beginning, random to top. And I claim it would work for the other chambers as well. And so this is something that Bidiger, Hanlon, and Rockmore noticed, and they noticed that other popular Markov chains could also be modeled on hyperplane arrangements. For example, you can kind of have a weighted version of random to top, where maybe you're more likely to pull 1 to the top versus 2 versus 3. So that can be any probability distribution. Or you can kind of do the more normal way of shuffling you might think of, where you break the card deck in half and then like interleave them. That's called riffle shuffling. And there's like a mathematical model of it that people kind of accept. And that turns out to be able to be modeled on the Braid arrangement in this way.
Patty, there's a question before you go forward.
Oh,
Sheila is asking, is there an orientation, or you can go, Sheila.
Oh, that's okay. I was just wondering if when you take your tiny step, are you orienting it in a certain way? Because that third example, the F3, you could go either way, right? For your tiny step.
oh, like why we should go this way instead of this way?
Yeah, right.
Yeah, I think you're going in whichever way is closest. So I think like to get to this chamber, you only have to cross over 2.
Okay.
But to get to this one, you have to cross over 3.
Right.
So I think it's, yeah, like you're taking the fastest path maybe. Yeah, I don't tend to actually work with this version of the multiplication because it's hard after n is bigger than 2. But yeah, I think it's like the fastest path.
Thank you.
Yeah.
I have a question. What if you start at the one-dimensional chamber, the one-dimensional face that goes from the center to the left, and you multiply that by the one-dimensional face that goes from the center to the right?
Oh, great question. So this one multiplied by this one?
Yeah.
Yeah, so you take the fastest path is like along this line. So you actually don't leave your face. It would still be like, so yeah, F3 times this one is still F3.
Oh, great. Thank you.
Yeah.
Yeah.
Yeah. So yeah, that's we're actually going to be thinking about multiplying kind of any element of the face algebra times chamber. So these are great questions. And so this is going to be like the more general setup here. So we're going to be interested in elements of the face algebra that have positive coefficients whose coefficients sum to 1. And so this might remind you of a probability distribution on the faces. And so this will produce a Markov chain on the chamber module just by multiplying the chambers by this element. And so we're going to call elements like this face shuffles. All right, so now we've encoded these shuffling operators in hyperplane arrangements, and that's interesting, but it might be better if we can actually use the hyperplanes to make sense of the eigenvalues. And it turns out that we can, and it has to do with something called the poset of intersections. So this is just as elements, all the intersections of the hyperplanes, and we're going to order them inclusion from smallest to biggest. So you'll always have a top to your poset, which will be the ambient space, and you can think of that as the empty intersection of your hyperplanes. And we're going to rate the top by 1 hat. And then you'll have like, you can try intersecting like 1 or 2 or 3 hyperplanes and so on. For our example, it's not super interesting because we have each of the hyperplanes intersected with themselves, but once you intersect any 2 of them, you get this origin in the middle. And this poset is actually going to label or index our eigenvalues for the phase shuffles. And so now we're ready to state the big BHR theorem. And so if we have a phase shuffle, it turns out that it's diagonalizable on the chamber module. The eigenvalues are indexed by intersections of hyperplanes, and we can compute them just by summing the coefficients of faces in our phase shuffle who lie inside that intersection. And there's also a formula for multiplicity. So if you've seen Mobius functions on posets before, it's just the absolute value of the Mobius function from x to the top. And I've attributed this both to Bediger, Hinlin, and Rockmore, as well as Brown-Diaconis, because Bediger, Hinlin, and Rockmore did this in the case where all the hyperplanes have to intersect in some point. But Brown-Diaconis showed it worked in general, and they also showed this diagonalizable part. So this is great because it takes care of a lot of maybe seemingly different Markov chains at the same time. And so we might wonder, like, can we generalize this any further? It turns out that yes, and the right setting to think about is left regular bands. So hyperplane phase semigroups are an example of left regular bands. And these are just finite semigroups which satisfy every element being idempotent. We call this a band. And then this kind of funny multiplication condition that, and we're going to call that left regular. And our main example for today of a left regular band will be the free left regular band. As a set, this is just words on the alphabet 1 through n without any repeated letters. And multiplication of words just means you concatenate them, but then you read from left to right and erase any repeated letters that come up. So let's do an example for n is 3. These are all the words without any repeated letters in the alphabet 1, 2, 3. And I should note that we even include the empty word here. And to do some multiplication examples, 2, 1 times 1, 3 just means we concatenate them, and then we read from left to right, but we see a second one. So we cross it out and get 2, 1, 3. Similarly, 2 times 3, 2, 1, we can delete this 2 and get 2, 3, 1. And something that this example hopefully motivates is that if you have U as any word and V as a length n word, you're going to get some potentially different length n word out because there'll be at least n distinct letters showing up. And finally, if you're multiplying by the empty word, you're writing nothing down. So it just acts like the identity. So this gives the free LRB a structure of a monoid. All right, so we've seen LRBs and we want to do a similar theorem to BHR. So we're going to need something to index our eigenvalues again. And it turns out the right notion here is something called a support poset. And this is given by the relation y is smaller than or equal to x, if and only if xy is x. And we identify elements that are smaller than or equal to each other. And we're going to call sup of x the image of x in this poset. So it's okay if you don't want to remember the precise definition, if you just want to think about the hyperplane intersection poset, or this next example we're going to do for the free LRB, which I think is even nicer. That's a great thing to keep in mind. So the support lattice for the free LRB turns out to be this familiar object, the Boolean lattice. So this is just the subsets of 1 through n ordered by inclusion. And the ways the support map works is we're just forgetting the order of the letters in the word. So I'm trying to like color code below an example for n is 3. And something we can note is that all of these length n words have the same support. Namely, they all have the support at the top of the poset, the set 1 through n. All right, and so once again, even though we've kind of introduced a semigroup, we're going to actually consider the semigroup algebra instead. And we need a notion of chambers again. We need to have something we can shuffle. And the thing we're going to use instead are the elements with support 1. And what's good about this is we saw with the free LRB, these were the words of length n, or like basically the same as permutations. So this is good again because it will, the permutations will represent all the ways to order our cards in the deck. And we'll kind of still use this like geometric language to describe LRBs in general. So we're still going to call these elements face algebras, and they're going to shuffle our chamber module in the same way by multiplication on the left. Okay, now we can see Brown's generalization of the BHR theorem. It should look very similar. Start with the face shuffle. It's still diagonalizable on the chamber module. The eigenvalues are indexed by supports. And we can compute the eigenvalues by summing coefficients of faces whose supports are contained in our chosen support. And the multiplicity formula is a little bit more complicated. It still involves Mobius functions of the poset. And I've kind of suppressed the meaning of this, but it's a function of y having to do with multiplication in the left regular band. But now we've seen this theorem basically 2 times, once for hyperplanes and once in this more general setting. So I think it's time to do an example and see how we can use this to make sense of the eigenvalues. All right, so let's try to figure out the eigenvalues of random to top and do this by thinking about modeling it inside of our free LRB. So I claim the correct face shuffle to think about here is this element that we're going to call x, the sum of all the 1-letter words divided by n. And I think this is not too hard to see from example. So if we apply x to our cards being in the order 1, 2, 3, 1 times 1, 2, 3, we delete the 1, we still get a 1, 2, 3. 2 times 1, 2, 3 becomes 2, 1, 3. And 3 times 1, 2, 3 becomes 3, 1, 2. So we see this shuffling operator being modeled again here. All right, so we have our face shuffle, we have the LRB. Let's think about the eigenvalues. I've put the relevant part of Brown's theorem above here. And remember, these are indexed by supports, which for the free LRB means subsets of the set 1 through n. So let's compute the eigenvalue that goes with the subset 1, 2. So just using this formula above, this is the sum of the coefficients of all words whose letters are contained in 1, 2. And some of these turn out to be 0. So for example, the empty set doesn't appear in our face shuffle, so that's 0. 1 appears with coefficient 1/3, as does 2. But these other ones, 1, 2, and 2, 1, do not appear. So our eigenvalue turns out to be 2/3. And I think if you did a couple more of these examples to yourself, you would see the general story pretty easily, which would be that for any support on the free left regular band, the eigenvalue that goes with S is just 1/n times the cardinality of S. And since these subsets can range from size 0 to n, this actually tells us the eigenvalues of random to top. It goes from 0, 1/n, all the way up to 1. And this was known previously by Fatterford in 1991, and this was before all this BHR theory came out. All right, so now we have the eigenvalues for random to top. Let's see if we can figure out how many times they appear. Okay, so I've again pasted the part of Brown's theorem that we'll need. And we're going to just do the 0 eigenvalue, but you could do others pretty similarly. So using his formula, this looks like this. If you're familiar with the Boolean lattice, you might know that there's a special formula for the Mobius function of it, which is just -1 to the size of that set. And I've kind of hidden the meaning of f of y, but I'm telling you it's turns out to be n minus size of r. And if you get a chance to look at the definition, I think you will agree quickly as well. And then if we just rewrite this sum in terms of summing over the sizes of the poset, or sorry, the sizes of the sets instead of the sets themselves, we get this sum, and writing it more explicitly, we get this. And so there's a chance some of you might recognize this formula. Does anyone happen to know what this formula counts?
Derangements, right?
Yes, derangements. Awesome. Okay, so yeah, this counts the derangement number. So derangements are permutations with no fixed points. And what we just showed is that the 0 eigenvalue has multiplicity equal to the number of derangements in Sn. And it turns out that if you did like the other computations, you'd be able to see this, is that the I/n eigenvalue has a nice multiplicity as well. It's just the number of permutations with exactly I fixed points. And one immediate implication of this is that this eigenvalue here is never going to show up, because if you have n-1 fixed points in your permutation, the last point is forced to be fixed as well. Oh, am I missing factorials? I looked at the chat. Yes, I think there should be factorials there. Thanks. All right, so yeah, now we understand the eigenvalues and their multiplicities. All right, so this is like all the BHR and LRB generalizations that I wanted to tell you about. But before we switch gears, I just wanted to quickly summarize some of the other work that has been going on in case you want to learn more. So it turns out that a lot of this, not everything, but some of it can be carried over to general bands. And this is work by Brown. Franco Saliola computed the quiver of the LRB algebra, and along with Margolis and Steinberg, also connected the representation theory of these LRBs to poset topology. And something that a lot of people have started studying as well is this idea of symmetrized BHR shuffles, where you take one of these shuffles that appears in the hyperplane arrangement and multiply it by its transpose. So there's been work to find the eigenvalues of these. All right. But now we're going to switch gears a little bit. And we're going to be motivated by invariant theory. So I think a typical setting here is that we have some group acting on a K algebra or a ring R. And often this is taken to be a polynomial ring, infinitely many variables. And a central question here is, what does the G invariant subalgebra look like? So these are elements of the ring who are fixed by the group action, and they're closed under multiplication. And another question we can ask has to do with the representation theory of the group. So formally, what we would be asking is, for every irreducible character of the group, what is the structure of the chi isotypic subspace of R, meaning kind of the collection of all the irreducibles isomorphic to chi, as a representation of the invariant subalgebra. And if you want, you could think about question 1 as a special case of question 2, where question 1 has to do with the trivial representation. And this is a little tricky to think about sometimes, I think, this way. If so, the language we're going to be using is a little bit more informal, which is, how does this ring look simultaneously as a representation of the group and the invariant subalgebra? So you can just think about this for intuition, but I guess precisely what we mean when we say that is this. And so there are several left regular bands that have a group action naturally attached. So at the beginning of the talk, we mentioned hyperplane arrangements. And if you're familiar with reflection groups or Coxeter groups, you might know that each of those has a corresponding hyperplane arrangement. And these groups will act naturally on the faces. So this is one such pair. The free LRB that we've been looking at today has an action of the symmetric group on the values of the word. And then in Brown's generalization of BHR theory, he introduces 2 different Q analogs of this free LRB, and both of them are acted upon by the group GLN-FQ. So something that we're interested in is, what do the answers to these classical invariant theory questions look like if we pick R to be the semigroup algebra of these LRBs and G to be their corresponding groups. And one motivation for this comes from the first case, the reflection arrangement case, because question 1 already has a really nice answer. In his PhD thesis, Bidiger proved that the invariant subalgebra of the face semigroup is anti-isomorphic to the descent algebra. And this is a well-studied subalgebra of the group algebra, especially in type A. And so we might wonder what happens with question 2. And this is a project I've been working on for some time now. And one thing that has been challenging about it is, even though the representation theory of the descent algebra is well understood, it's a little complicated because it's not semi-simple, which is causing some difficulties. But something that has been helpful for making progress is answering these same invariant theory questions for a different LRB, namely the free LRB that Sarah and I and Vic have been working on. So we've answered these questions for the free left regular band, and we've started to think about it as well for Q analogs of these free left regular band. All right, so let's jump into our research then. So the invariant subalgebra turns out to be spanned by sums of words of the same length. This might not be so hard to see because you can think about like the SN orbit of these words will maintain the length. So we're going to call xi the sum of words of length I. But something I think will be more surprising is that it turns out that it's actually also spanned by the powers of this element x1, the sum of length 1 words. And this should be exciting because this looks like the face shuffle we saw earlier. This looks like the random to top face shuffle on the chambers. And so we put an example below for n is 4 of the change of basis matrix between these two bases. And it's a nice matrix. Everything that doesn't have a number, I mean that to be 0. And there's just ones along the diagonal. And there's a chance that you might recognize these coefficients here as well. Does anyone happen to recognize the triangle?
Sterling number of the second kind.
Yeah, exactly. Yeah, these are Stirling numbers of the second kind. And so it turns out that we could show that there's a nice multiplication formula for x1 times any of the other xi's. And this looks a lot like a Stirling number recurrence. And so that helps us show that this is the change of basis matrix. And then that is going one direction. If you want to go the other direction, you can use that the like Stirling numbers of the second kind and the first kind are inverse. And so these going the other direction involves Stirling numbers of the first kind. And so if we use these formulas, we can actually show very explicitly the ring structure of this invariant subalgebra. So it is just a polynomial ring generated by one variable, modded out by this ideal. And the variable of importance here is that x1 that popped up with random to shuffle or random to top. So since this generates the subalgebra multiplicatively, we're going to drop the subscript to make our lives easier and just call it x. And something we should note is these formulas for like the transition matrices and things like that were previously also found by Garcia, and he was studying powers of the top to random operator, which is the transpose of the random to top. All right, so that kind of answers our question 1. What does the invariant subalgebra look like? And now we want to answer question 2, which was this simultaneous decomposition of the free LRB algebra over as a representation of both the symmetric group and the invariant subalgebra. So to do that, we might need to know what the representation theory of this invariant subalgebra is. And this can all be gathered from this ring structure here. But it turns out, yeah, it's semi-simple. The irreducible representations are all one-dimensional. They're just involving x scaling by these numbers. And these should also kind of look familiar. These are up to scaling by n. These are the eigenvalues of random to top that we saw. And so really, like if we have some representation of the subalgebra, understanding that representation just comes down to knowing the dimensions of these eigenspaces for these eigenvalues. And we're going to call like the J eigenspace kernel of x minus j restricted to that space. So our simultaneous decomposition comes down to this following equivalent goal, which is understand the eigenspace on the free LRB algebra as SN representations. All right, so The first thing we're going to do, and this turns out to be kind of the seed of everything, is think about what the kernel of X is like on just the chamber submodule. So like we saw earlier, X up to scaling acts like random to top on the chambers. And we saw that the dimension of the kernel was the number of derangements in Sn. So this is some Sn representation whose dimension is the number of derangements. And it turns out that this has been studied before. Disarmanian and Walks first introduced the corresponding symmetric function, and later Reiner and Webb found a representation theoretic interpretation and gave its decomposition into irreducibles. And it also appears in other works as well. So the way the decomposition works has to do with something called the first ascent of a standard Young tableau. And this is the smallest value k, such that k plus 1 does not appear in the first column. So let's do this example here. You'd start with 1, and we go up the next number 2. Does 2 appear in the first column? Yes. So we'd try 2 next, go up 1 number, 3, which does not appear in the first column. So the first ascent in this example is 2. And so the way to get the derangement representation is to write out all the standard Young tableau that have an even first ascent, and these will contribute their shape to that derangement representation. So here are some examples of the derangement representation. These are irreducible decomposition into spec modules. So for instance, if you were to write out all the standard Young tableau of size 3, you'd find that just one of them has an even first ascent, and it's of this shape, which means the derangement representation will be of that shape. Oh no, we are somewhere. I'm going to scroll ahead. I think I got pushed back to the beginning. Okay, cool. We are here. And yeah, so that was step 1. It was the kernel on the chamber module. And the next step turns out to be, what are the other eigenspaces on that chamber module? And it's going to involve this operation on SK representations, which is just tensor it with a trivial of the size n minus k and induce up to Sn. So if you like to think about things in terms of symmetric functions instead, this is just like multiplying by an h n minus k. And so if we use again that X acts like random to top on the chambers, it turns out that this is just an induction of a smaller derangement representation. And this follows from previous work by either you could use Uyemura-Reyes or Reiner Walks, who both studied these J eigenspaces of random to top. Uyemura-Reyes did it in terms of the higher Lie representations. And if you kind of break this down into its symmetric function counterpart, you can see this like multiplication by an hn minus k. Or Reiner and Walks did this combinatorially with Tableau. They, for every Tableau, kind of categorized which eigenspace it belongs to, and their categorization shows that it does have this like inductive structure. So our main contribution is then doing it for the rest of the semigroup algebra. So really, like all the theory so far focuses on what happens in the chambers. But the chambers are what we're getting shuffled. People understand the eigenspaces as representations on the chambers. But you really could shuffle the whole LRB algebra if you wanted. So for instance, you can multiply X times any word. It's a little bit more complicated because you get some words of different lengths, but it can still be done. And so, yeah, our main result was to find the SN decomposition of the eigenspaces for the whole semigroup algebra. And what's really neat is that it also ended up just coming down to some inductions, like with some sums of just smaller derangement representations. So everything kind of stems from this small representation. And so as an example, we have like the one eigenspace here. You'd sum over like LS1 and LS2. And so I think this would really, oh, yeah. And so because the derangement representation for one actually turns out to be 0, there are no standard Young tableau with even first ascent. We can just restrict our attention to the LS1, which tells us that this is inducting up from the empty representation, like 2 steps. So kind of adding a box to the empty set in all possible ways, which would give you, or first adding one box and then adding a second in both ways, which would give you this S2 decomposition. All right, and maybe since we have a couple minutes, I will say something else that we looked a little at without going into too much detail is projective resolutions of the trivial module for the free LRB algebra. So in their work, Margolis, Steinberg, and Saliola construct a projective resolution for all the LRBs, and it has to do with taking a certain poset, turning it into a simplicial complex by taking the order complex of that poset.
Right.
And then this simplicial chain complex turns out to be a projective resolution. And the exciting thing here is that if we use a different kind of inductive structure, so you can think about this as multiplying by an h1 to the k instead of an hn minus k. Or sorry, an h1 to the n minus k. And I think this should be an n minus k. It turns out that all the like structure again here comes up to inducing this derangement representation up in different ways. So just to summarize, there is a lot of interest in left regular bands because there's they give a unified way to compute eigenvalues of lots of Markov chains. And some of them have an extra structure of a group acting on it. And we can ask more questions in this case. And in the case of this free left regular band, the story is very nice. It all ends up boiling down to just the random to top shuffling operator, and then figuring out how to induce this derangement representation up in various ways. So other than that, I have the references if you were interested in looking at any of the papers I mentioned. But thank you for listening, and I'm happy to answer any questions.
Let's give Patty a round of applause for that awesome talk. Okay, so questions.
Oh, well, I say thank you for it looks like it's a very interesting, deep subject with a lot of connections. So I have maybe a naive question. In the last few slides, could you review or explain what the kernel of x minus j is? You know, how is x minus j an operator so that it has a kernel?
Yeah, so yeah, this is really like x minus j times the empty word, I guess, is there's like a 1 in the monoid. And so this is an element of the face algebra. And so if we rewrite that as x minus j, this kernel here is the same as the j eigenspace of x acting on, well, I guess on any piece of the semi-group algebra.
Okay, I guess I need to go more elementary. What is X?
Oh, sorry. Yeah, x is the element 1 plus 2 plus.
Oh.
It's that. Yeah.
Okay. So X minus J is the sum of the numbers except for J.
So x minus j would be the sum of these numbers.
Yes, it's 1 plus 2 plus n missing J.
Actually, that is what it looks like now that I see it. But I think what we really mean is minus j times the empty word. So like minus j times R1. So I see that this is a little misleading, the j here. But yeah, this is what we mean by x minus j.
Oh, the empty word. But wouldn't 1 plus 2 times n times the empty word? That would be 1 plus 2. Okay. I don't understand. Why is the 1 plus 2 plus n? What's the difference? What's the difference between say 2 and j times empty word? Yeah, in other words, what's the logical distinction between, say, one of those integers in the sum, like 2?
Is it that those are letters?
Yes, these are. Yes, thank you. Yeah, these are letters. So. Yeah, so 2 times, for example, the chamber 1, 2, 3 would be 2, 1, 3, like concatenating them and
I see.
Repeated, versus j times epsilon, j times the empty word of this would be j times that. That's a great question. I realized, yeah, this notation is could be interpreted in a lot of ways.
So j is a variable for a letter.
Yeah, j is a constant.
Yeah. So j might be 3.
J might be 3, yeah.
Okay, so 3 times the empty word times 1, 2, 3 is 3, 1, 2.
You said 3 times the empty word times 1, 2, 3.
Yeah.
Is so that would be 3, and then you write nothing, and then you write 1, 2, 3, and eliminate the 3.
Yeah, right. 3, 1, 2. Okay.
Okay. Yeah.
Okay. Yeah.
Thank you for asking about that.
But similarly, word 2, word with one letter 2 is equal to a word with the one letter 2 times the empty word.
Yeah, the empty word is really like the identity in the mono.
Yeah,
so yeah,
okay.
You can multiply anything times it.
Okay, so we don't really, when you write the j times empty word, you don't really need to write empty word.
Yes. So that's, I think, yeah, what we meant is a j times like 1. But yeah, you're right that this is a number versus these are letters.
What? No.
I want to make sure that that there's a chance for other people.
Okay, yeah, thanks. I can look at the references.
Let's revisit this at the end. I'm happy to stay in the room and keep it open. Do other people, but these good question. Do other people have questions?
I had a question. So we noticed that KFN to the SN, so that was a little back, was generated by these element to random to top shuffle, or this random to top element.
Yes.
So this operator, like it's a shuffle, and presumably I can get to any shuffling of the deck from it. Do other shuffles have this property that they could generate this?
Oh, like, is this the only generator for this?
Yeah.
That's a good question. I don't know. Yeah, I guess there might potentially, there might be,
Sure.
well, yeah, I don't know. This is the one that that comes up like in this isomorphism, and
Right.
it's
And
a,
it's probably a nice one to work with, so it makes sense to use it. But I was just wondering if this was maybe a property of being some kind of shuffle. And so if, say, you took the riffle shuffle operator, would it do something similar?
yeah, so I actually don't know if you could model the riffle shuffle on the free LRB. You can definitely
Okay.
do it on the hyperplane arrangements like we
Sure.
had, but I don't know of a way. There might be one, but that it comes up with the free LRB.
Okay, thank you.
Yeah, good question though. Thank you.
Any other questions for Patty? All right, let's give her another round of applause for a great talk. And I guess we can stop the recording. Maybe we already did.